Hello coders, I'm about to show you a code that looks perfectly reasonable, compiles without errors, but has a hidden ghost that can make it defy logic itself. Watch what happens when I run this. So the main thread clearly sets stop equal to true, but the worker thread keeps running forever. How can a variable be both true and false at the same time? This isn't magic. This is real hardware behavior that every professional developer must understand. And here is the scary part. Your production applications might have this exact bug hiding in them, waiting to cause midnight outages. So lean in, open your minds, and get ready to see the invisible forces that control your multi-threaded applications, because in the world of concurrency, what you don't know will hurt you. This Java code demonstrates a memory visibility problem. The code has a main thread and a worker thread. The main thread sets a shared variable stop to true after waiting for 100 milliseconds, and the worker thread is supposed to break out of a loop when stop becomes true. However, worker thread may never see the update to stop and thus run forever. To fix this code, we must understand what memory visibility is, what compiler and CPU optimizations are, and what is the happen before relationship. Let's first go over the fundamentals of CPU and memory architecture. In multi-core CPU systems, registers, caches, and RAM form a critical memory hierarchy. This system is carefully designed so that data is moved seamlessly between these levels, with the fastest and smallest memory holding the most frequently used information. Starting at the top of the hierarchy, CPU registers. CPU registers are the absolute smallest and fastest memory components built directly into the CPU core itself. They operate at CPU's full clock speed, meaning access is nearly instantaneous. These are typically measured in bits, either 32 bits or 64 bits, or just few bytes. Their primary function is to store specific data and instructions that the processor is actively executing at that very moment, such as operands for an arithmetic operation or a program counter which holds the address of next instruction. Moving down one level, we encounter CPU caches. Caches are high-speed on-chip memory buffers that store copies of frequently used data from RAM. Their purpose is to reduce the time the CPU spends waiting for data. L1 cache. The L1 cache is physically integrated right into each CPU core. It is the smallest, typically between 32 KB to 128 KB per core, but also the fastest of the three cache levels. It's usually split into two separate parts: an L1 instruction cache and L1 data cache, which stores the actual data. L2 cache. The L2 cache is still located on the CPU chip, and it is exactly dedicated to each core, though sometimes shared between a couple of cores in specific designs. It's larger than L1, around 256 KB to 1 MB, per core but slightly slower. It effectively acts as a bridge between L1 cache and shared L3 cache. L3 cache, which resides on the CPU chip again, but it is generally shared among all CPU cores. This is the largest cache level, often ranging from 4 MB to 50 MB or more, making it the slowest of three cache levels. It acts as last checkpoint before fetching data from much slower main RAM. This shared access is vital in multi-core system. It helps maintain what we call cache coherency, ensuring all cores see consistent view of the memory. We will actually talk about cache coherency in much more detail later in this video. Finally, we have RAM, which is the main working memory of the entire computer system. Located on the motherboard, separate from the CPU itself, it is significantly slower than any level of cache memory. Access latency can be over 100 CPU cycles. RAM stores the operating system, all currently running applications, and the data that is currently in use. When a needed piece of data is not found in any cache level, an event referred to as a cache miss, the CPU then fetches it from the RAM. So how does all this work together? Here is the typical data access path. When a CPU executes an instruction, it first tries to fetch operand directly from its register. If that data isn't in register, a register file miss, the CPU immediately requests it from L1 cache. In the L1 cache, if data is present, that is cache hit, it returns to the PC register in few cycles. If not, that is cache miss. The request immediately proceeds down to L2. This pattern continues. An L2 miss triggers a request to L3 cache, and L3 miss forwards the request all the way to main memory. Once the data is fetched from main memory, it incurs high latency. It is then propagated back up the hierarchy, populating all the caches along the way. Here data is transferred between memory and cache in fixed size chunk, which is called as cache lines, typically of 64 bytes. Make mental note of those cache lines here. We'll need this specific concept when we discuss false sharing in future segment. So that's high level overview of your system architecture. Now let's talk about the Java memory model and how it relates to the hardware architecture we just discussed. Let's imagine a scenario where we have two threads operating on dual core CPU system. Thread 1 is running on core 1 and needs variable A and B to perform A plus B operation. Thread 2 is running on core 2, needs variable C and D to perform C minus D operation. In this ideal setup, the data flow is smooth because thread 1 only needs the data residing in cache line X and thread 2 only needs the data in cache line Y. The data flow looks something like this. Thread 1 requests variable A and B from main memory. Core 1 fetches cache line X from RAM and loads a copy into its local CPU cache. Core 1 performs A plus B operation efficiently using its local cache copy. Concurrently, thread 2 also requests variable C and D from memory. Core 2 fetches cache line Y from main memory and loads it into local CPU cache. Core 2 performs C minus D operation using its local cache copy. Both operations complete efficiently and in parallel because each core accesses its own independent cache lines, avoiding any contentions or communication overhead. Now, what happens if there is only one shared variable that both threads are working on? For example, a shared stop variable we used in demo. This is where things get complicated. First, it's important to understand how threads start at low level. When your main thread executes worker thread.start method, several things happen behind the scenes. Control transfers from Java code down to the JVM C++ code. The JVM calls native operating system functions like pthread create in case of Linux and create thread on Windows. The operating system allocates a necessary kernel thread structure. The operating system sets up thread stack in memory, and finally operating system scheduler places that newly created thread into a ready queue, and when scheduled, thread begins executing on an available CPU core. The reason I'm explaining this flow is to highlight a key concept. Every traditional Java platform thread is mapped one-to-one with an underlying operating system thread. Each of these operating system threads has a significant memory overhead associated with it. It's worth noting that when we talk about virtual threads introduced in Java 19, this traditional one-to-one mapping changes to M to N mapping model, that is many virtual threads to small number of carrier threads. But for our current discussion, we'll stick to the traditional platform thread model where JVM manages the mapping but the operating system handles the actual scheduling. So we have two operating system threads, main thread and a worker thread. Imagine main thread fetches the shared variable stop, which is initially false, into its CPU cache. It then updates that local value to true. At almost same time, the worker thread might fetch the value of stop into its local CPU cache where the value is still original false. Here is the crucial point. For worker thread, the value of stop in its local CPU cache remains false, so it's keep running its loop indefinitely. However, for main thread, variable has been updated to true, but that change is still sitting in its local CPU cache and is not immediately visible to the worker thread on the other core. This highlights exactly why it is essential to understand Java memory model if you want to design correctly behaving concurrent programs. By now, You must have understood the foundation of the Java memory model, and be ready for part 2, where we'll discuss the solutions including the volatile keyword, synchronized blocks, and the happens before relationship. If you found this video helpful, please give it a thumbs up and subscribe for more technical content.